this series on supersymmetric quantum mechanics. I'm going to start with this first lecture on what is supersymmetry, and then we're going to see that why supersymmetry is needed at all, and then we're going to look at the basic harmonic oscillator in the fermionic case, and then I'm going to quickly jump into the supersymmetric harmonic oscillator. And in the following lectures, we are going to look at the supersymmetric systems using the Hamiltonian approach, and we'll also work with the hydrogen atom using the supersymmetry. We'll also be looking at hopefully the term supersymmetry breaking. Right. So, let's start with the question, what is supersymmetry? Right. So that's the question that we'll try to answer first. And let's start with the fact that we can classify particles using statistical mechanics. So I'm going to use shorthand notation SM for statistical mechanics. And you know that in statistical mechanics, you classify particles on, you can write the, what is that called? The occupation number, right? And the particles are classified in two categories. For our purposes, two categories. We have first we have bosons, and then you have particles that are classified as fermions. So, if you are watching this lecture, you already know in somewhat detail about what is a boson and what is a fermion and why are these two different classifications. So first of all, we know that we know what bosons are, right? You know that if you have a bunch of bosons, they can sit or occupy a same quantum state. So, let me just give a heading and quickly discuss what bosons are. So, they can occupy a same quantum state. So, there is no restriction on their occupation, right? So they can there can be number of bosons in a single quantum state, and these bosons, they'll satisfy, or they follow what is called Bose-Einstein statistics, right? So you can define that statistics using the occupation number for bosons, which is n, which is equal to there is an I index over here, and it's summed over that index I with this GI, which is the degeneracy factor, which you have to account for in bosons, and then you have exponential EI over KBT minus 1, right? And this is also known as the expectation value of the number of bosons at energy EI, right? Okay, so you know all the terms over here, right? K is the Boltzmann constant, T is the temperature, and G is the degeneracy factor. And so if I were to write the bosonic wave functions, for example, let's say that you have a bosonic wave function psi b1 for boson 1 and psi b2 for boson 2. And if I were to interchange these bosons, you would have the same thing, psi b2, psi b1. So there is no change of signature, right? So if it was initially plus psi b1, psi b2, you'll still have plus psi b2, psi b1. So I just interchanged these positions here, and there was no effect on the signature. So they are both identical, right? Okay, so, and we also know another thing about bosons, that they have integer spin, right? So if I were to write spins for bosons, it could be 0, 1, 2, 3, and so on. So this is integer spin. Right. Now, if I were to give you an example of a boson, a very popular example is of a photon, right? So a photon is a boson. Moving on, and let's not get into the very gory details of what bosons are. I would expect that you already know about this. So let's quickly also discuss about fermions. And well, what are fermions? We can use the same approach of describing them. Fermions, they will strictly follow what is known as the Pauli exclusion principle, and I'm sure that you all know what the principle states, right? And it's just you can state the principle in many ways, but one of the way is just saying that a very basic way is saying that there are no two fermions that can occupy a same quantum state. So the first thing that is different, and it's in fact the opposite from the bosons, it is that how do I write this? No two fermions can occupy same quantum state, right? That's basically what Pauli exclusion principle says. And these are again classified using the expectation value of the number of fermions, and this is known as the Fermi-Dirac statistics. And in this case, the degeneracy factor is just 1, right? And then you have e to the ei over kbt minus 1. Actually, there is a plus 1 over here for Fermi-Dirac statistics, right? And well, if I were to now interchange the wave functions for these fermions, right? Let's say you have a fermionic wave function psi f1 and psi f2, and if I were to interchange these, I would get a negative sign over here, and then psi f2, psi f1, right? Okay, and this is a very important property for classifying or defining fermions. And well, if I talk about their spin, they have a half integer spin, which is just that the spin would be something like 1 by 2, 3 by 2, you'll have 5 by 2, and so on, right? So it will be always an integer multiple of 1 by 2, right? Okay, and a very popular example over here is an electron, right? Okay, cool. So now, knowing what, or at least revising what bosons and fermions are, let's dive into supersymmetry, right? So why did I talk about fermions and bosons? I'll just tell you right now, okay? That's what supersymmetry is. So a supersymmetry is actually a symmetry between fermions and bosons, right? So what that means is that if I have a boson, I'll write it in a ket state, and I had to go from boson to a fermion state. Supersymmetry allows that, right? And it allows that in a way that if I were to have a supersymmetry generator, and let's call that supersymmetry generator Q, right? So Q is a supersymmetry generator, and I called it Q for a specific reason, because this supersymmetry generator is known as the supercharge. So the generator for supersymmetry is called a supercharge. And if I were to take this supercharge and act it on a bosonic state, it would take me to a fermionic state. Now note that you have the bosonic state is an integer spin, right? So in a bosonic state you have, for example, you could have spin 1, 2, 3. So it's an integer spin, and you're going to the fermionic state, which is a half integer spin. So so what does that tell you about Q, about the supercharge? It tells you that the Q supercharge, it should have a half integer spin, right? And only then you can, if you take a half integer spin and act it or compose it with the bosonic state, you would get a half integer spin, right, which is a fermion. Right, sorry, I had to leave. Okay, so where was I? Right, so you have one information about this Q, that it is a half integer spin, and knowing that it is a half integer spin, you also know that it is then, well, this itself implies that Q is a fermionic generator, right? Which is or which should be obvious, because if you take it and act it on a bosonic state, you receive a fermionic state, right? Okay, so well, that's this. Well, now moving on, so far we have in a way answered the question of what is a supersymmetry, and now let's move on to why do we need supersymmetry in the first place, right? So the next question that we will look at is, why do you need supersymmetry, right? And to answer this question, we have what is known as a Coleman-Mendola theorem. Hopefully I'm pronouncing that right. So, and hopefully I'm writing the spelling right as well. And this theorem essentially or basically states that if I have a quantum field theory, right? So if I have a quantum field theory and I'm looking for the scattering matrix, right, which is also called as the S matrix, this S matrix is going to have some properties, right? And the properties that it has are it satisfies locality. It also satisfies causality and locality, right? And well, there are more, and well, Now let's talk about this Coleman-Mendola theorem, and it states that if I have a quantum field theory and I want this scattering matrix and this S matrix, there will be only a limited number of symmetries, right? The S matrix will only have a limited number of symmetries, and those symmetries are well, let me write it down. The symmetries will be the Poincare symmetry, and which is basically the symmetry of translations, and you have the Lorentz symmetry as well. So what this essentially means is that the maximum space-time symmetry that you can have is known as the Poincare symmetry, right? And you can also have symmetries that are internal. So I'm just going to write internal symmetries. Well, you know them, like for example, the gauge symmetry or a global symmetry, right? And note that this statement, or this Coleman-Mendola theorem, it is a very restrictive theorem because it is telling you what you can or what you cannot have, right? So so when Coleman and Mendola proved their theorem, they used or they assumed that these symmetry generators, all of them, were bosonic in nature. But what if I were to go a step ahead and I include the fermionic generators as well? What happens? What happens then, right? So I can extend their theorem, and now the maximum allowed space-time symmetries are you'll have this Poincare symmetry, and you would also have the what we are talking about, the supersymmetry, right? So SUSY, right? So because including the fermionic generator allows you these two symmetries, and they are the maximum symmetries that are allowed, and unless that one of them is ruled out, and it's not so far. So the beauty of physics is that if you have something and the possibility is not, well, discarded or something, then it being true, there's a very high chance, right? And so one of the biggest motivations of understanding or of introducing supersymmetry in the first place is this reason itself, right? So well, a super well, there are more reasons, right? And this is one of the main motivation, and you'll also see foregoing in this series, or even in this lecture, the supersymmetric Hamiltonian is also it's also positive, right? And that means that it will only give you the positive energy solutions, and that is a plus one for us, because well, negative energy solution means that the theory is not stable, or it's unstable. And well, because supersymmetry gives you positive energy solutions, that means that it is already implying that the theory is stable. And so, well, that is again another one of the reasons that you are supposed to understand supersymmetry, right? Okay, now Now let's move on to the bosonic harmonic oscillator, or let's keep this video as an introduction to supersymmetry, and we'll talk about bosonic harmonic oscillator and then link it with the supersymmetric harmonic oscillator in lecture number 2 or in the next video.